Okay, well, first of all, guys, once again for Monday. 4 years teaching this class, it's the first time I've done that in my defense. I went to do my taxes and realized I did not have my wife's W-2 and realized it was still in Durham, and one thing led to another, and yeah, so basically, this was going to be Monday's lecture. I moved it to today because I know Sarah was interested in it, among others. And Monday I just did survival analysis, which so far nobody has expressed interest in. And I haven't created the YouTube for that lecture yet, but it'll be there. I very highly doubt that anything from that lecture will be on the final. So if you want to just ignore it, that's probably fine. But I'll put it up there so that nobody feels like they're not getting their money's worth out of this class because of my flakiness. Yeah, if anyone turns in homework late, you can just like say, well, at least I show up for class, Eric. Anyway. Mixed effects models. Pretty much everything we've done in class thus far, I've said over and over again that don't try this particular test or this particular method unless your data is independent. And generally speaking, when you're trying to do statistical analysis, if your data is not independent, you're just about dead in the water. T-tests don't work. Bootstrapping, there's ways that you can make bootstrapping work, but the bootstrapping that I've taught you in this class doesn't work. Chi-square tests don't work. Your regression assumptions get violated. Basically, non-independence is bad. And in general, if you have data where the independent assumption is violated, getting around that is a really tricky problem. Your best bet is to talk to an expert who deals with that type of data, because you can get into major trouble if you try to resolve it on your own. But there is one particular special case where the lack of independence is less problematic. That the place where independence is relatively easy to correct for is if you have repeated measures on a given experimental unit. Say, well, a couple examples that we've considered in this class or that people have discussed with me in real life. You say, for example, you go to the doctor's office, they measure your heart rate twice to make sure that you get an accurate reading. Or say you're raising mice in the lab and you weigh them once per week for an 8-week period, something like that. Or you're doing an experiment on cell lines and you culture each cell line in triplicate, and so you get 3 measurements for each cell lines. And the key nature of this particular design is that across experimental units, the independent assumption is still satisfied. Mouse A is independent of mouse B, and cell line A is independent of cell line B. But within an experimental unit, obviously they're not independent. If you have the same cell culture evaluated in triplicate, then you would expect that if the value of the measure of interest is high in the first plate, that it would be high in the other 2 plates as well, so they would not be independent. I mean, one relatively brain-dead solution for this is you can just average the measures across a given subject. And we've briefly discussed that in a couple examples in class thus far. And I mean, particularly if you only have like 2 measures per subject, I mean, it's really not a horrible solution. But it's not an ideal solution for a lot of problems, particularly if you have a large number of repeated measures for each subject. Say, for instance, you have like, you weigh your mouse once per week over an 8-week period. Well, then you have 8 data points for each particular mouse. And if you have something like 6 mice, then if you just naively average, you go from a data set with size 48 down to a data set of size 6, which just taking the naive averaging approach, that's going to result in a major loss of power. And it also obviously can account for variation over time. Presumably, if your mice are born at the beginning of your experiment and you measure them over an 8-week period, well, they're going to get larger over the course of that 8 weeks. And if you just average, you completely lose that information. And it's particularly egregious if you have other variables whose value measures over time. Say, I don't know, for instance, the amount that the mouse eats or something like that. They may eat more as they get larger, and that may vary from mouse to mouse. If you simply average all your data, you lose all that information. So for all these reasons, in general, averaging is not a satisfactory solution to this problem. A better way to deal with this is to do the methodology I'm going to discuss today on mixed effects modeling. Oh, if you'll recall our ANOVA model from a couple weeks ago, that the basic ANOVA model is if observation I belongs to group K, then the value of observation I is equal to the overall mean across the entire study plus an offset for group K plus a noise term. And your null hypothesis is that all of your noise terms are equal to 0, implying that the means are the same for all the different groups. And mixed effects ANOVA is very similar to two-way ANOVA that we discussed previously, but in this case, say we have n subjects that are divided into m treatment groups, and the assumption here is that between subjects the data is independent, but within subjects the data is most likely not independent, and we want to test the null hypothesis that the means across the different treatment groups are the same, taking into account the within subject variability. So what's the model for that? The usual model is actually very similar to the two-way ANOVA model, that we assume observation I comes from subject J and belongs to group K. So K could be treatment versus control. J would be like which mouse the data is collected from. Well, in this case, you're saying the model is that the observation I is equal to the overall mean plus the offset for group K, whether you're a treatment or control, plus a random effect term for which mouse the data is coming from. And we want to test the null hypothesis that all of these offset terms are equal to 0, the cases are equal to controls, or whatever the case may be. And if you look back a few lectures on two-way ANOVA, you'll see that the model on the previous slide is very close to the two-way ANOVA model. That, in fact, if you replace tau k with, I forget the notation I used in the other lecture, but otherwise, if you replace bk with whatever I used for the second fixed effect in the other lecture, it's identical. So what's the difference between the two? Well, the idea is that fixed effects are assumed to be a fixed number. We can't observe it, so we have to estimate it. We assume it's some fixed thing, that if you're treating your mice with some growth hormone, the growth hormone increases average growth by some fixed amount that we're trying to estimate, but it's not random. On the other hand, random effects are assumed to be random variables. In this case, the random effect of the mouse is that some mice are a little bit bigger, a little bit smaller than others, whatever the case may be, and that little bit bigger, a little bit smaller term is just another random noise term that varies from mouse to mouse. The basic idea, if you go back to this slide, is the BJs are the error in the model associated with a given mouse, the fact that some mice are bigger or smaller than others, and the epsilon is just the completely unexplainable error that can't be attributed to variation from mouse to mouse or anything else. It's just unexplainable noise. And so this raises a question when you're fitting these models, how do you know if a particular term should be modeled as fixed or modeled as random? If you remember the two-way ANOVA models from a couple weeks ago, we had like the effect of which type of nitrogen fertilizer you use and the block, the section of the field where the fertilizer was allocated, and I had modeled them both as fixed. Why was the region of the field where the fertilizer was used considered to be fixed rather than random? And I mean, honestly, in some cases, it's a bit of a judgment call, and the results probably wouldn't change drastically however you did it. But the general rule of thumb, if you're unsure, is that if increasing your sample size will increase the number of levels of a variable, then it should be treated as random, whereas if it won't affect the number of levels of your variable, it should be treated as fixed. So if you take this example I've been using with the mice that are treated with the growth hormone, say you initially have 6 mice and you get 6 more mice. Well, the 6 additional mice, they'll either be in treatment group or control group. Treatment versus control, there are 2 levels regardless of how big your sample is. So you would probably want to model treatment as a fixed effect. Whereas if the effect of the mouse, if you go from 6 mice to 12 mice, well then obviously you have 12 mice. So there are 12 different levels for the mouse variable rather than just 6. So in this case, you would probably want to model the mouse as a random effect, because if you recruit more mice, there are more possible levels for the mouse variable. So hence you should regard it as random. Or in general, you think it's just like a variable that's just contributing a source of error, and you could get more levels of that variable as your sample increases, you can model it as random. And I mean, honestly, most of the time, if you're just comparing treatment versus control, if you model the mouse effect as fixed or random, it won't make a huge difference. And I mean, if you're ever unsure, you're welcome to shoot me an email or some other statistician you work with an email. But that's the general rule of thumb here. Hmm? Mm-hmm. A what? An inchworm. Thank you for pointing that out. Oh, it's fine. I remember one time I was sitting in a lecture in undergraduate, and like the professor had this huge wasp on his arm. I was kind of like, ah! Yeah, anyway, so. Glad I caught that. Oh, geez, now it's. Okay, there, gone. So, going back to this example, this is a data set that's built into R of where they were trying to measure the amount of protein in cow's milk. And each cow in the study was fed one of 3 different types of diets, either barley, lupins, or both barley and lupins. And the question was, does the feed type affect the amount of protein produced? And the protein levels were measured at various different times. They didn't just collect this once. I forget exactly how long the study went for, but they collected some milk like once a week or something like that and measured the amount of protein in the milk each time a measurement was collected. And the question was, does the feed type affect the amount of protein produced, taking into account that protein levels vary considerably from cow to cow? And The simplest way to do this in R is to use a command called LME that's part of a library called NLME. You won't need to install this package, it's built into R, but you will need to use the library command to load it. And I will note in passing, this package is now deprecated. There's a new package that at least the authors of this package say should be used rather than NLME. The reason I don't teach the new package is because, well, I guess maybe I should explain that here in a second. Basically, the new package doesn't give you these p-values, and that's primarily what you're interested in most of the time when you do this analysis. So, personally, I still use NLME for most things just because I know those p-values are problematic, but they're what you want to know a large percentage of the time when you do this analysis. So I just ignore the fact there's problems calculating these p-values and use them anyway, as do many other people. But if you're ever trying to do this type of analysis on a very large data set, for instance, you may want to think about using the new package, and you're welcome to shoot me an email if you need help with that, because the new package is much faster. But for small-scale data sets that you deal with most of the time, the NLME package is fine. And the notation here is a little bit odd. I'll try to explain it the best I can. The command in R to do this is called LME, which stands for linear mixed effects. It's similar to the output for, it's similar to the notation for an LM model. You have your output, in this case protein, amount of protein in the milk, twiddle, whatever your predictor variable is, in this case diet. And you can give a data command just like you can for an LM object. The one thing that's new is this random command, which says random equals twiddle1 line cow. What does that mean? That basically says fit a random effect for each cow. And the twiddle1, what that's saying, I'll try to explain this in more detail later on, but it just basically says fit a random intercept for each cow. In other words, we assume that the mean protein levels vary from cow to cow, but that's the only thing that varies from cow to cow. Nothing else varies. There's nothing that determines the variation from cow to cow other than the cow itself. Yeah. Hopefully I can explain this more clearly when we do a more complicated model. If, for example, you think the protein levels vary over time for each cow, you could say random twiddle time line cow, and that says basically fit a different random slope to each cow sort of thing. But one way or another, you get a model, you'll get output that looks something like this, and it's basically the same. And you read this output the same way you would output from the LM object. In this case, diet is a factor. It automatically chooses one level of the factor. In this case, barley is the baseline. So the interpretation is the mean protein level is about 3.526 for those that get a barley diet. If you get both barley and lupins, then the protein level is about 0.096 smaller. And if the cows that get lupins only, the protein level is about 0.2 smaller. And it looks like the effect of lupins is significantly different from barley, and barley and lupins combined is a little bit lower, but not statistically significant at the 0.05 level. It's close, though. So hopefully, in terms of interpreting the model, it's not radically different than what we've done already. In general, if you say LME y twiddle x and say random equals twiddle 1 line group. That'll fit a mixed effects model to predict y based on x, where group is the grouping variable, and you can pass it to summary to get pretty output just like you can for LM and other similar functions. And as I just alluded to, this previous model, it assumes the protein of a cow's milk doesn't vary over the lifetime of a cow, which in practice isn't likely to be true. And so we might want to model the effect of time, say, not only is there variation from cow to cow, but for a given cow, it may produce more protein early in its life or late in its life or whatever the case may be. Oh, the simplest way to model that is that you simply include a term for time in the model that you say the amount of protein produced by the cow is equal to an effect of diet plus an effect of time. In this case, diet is still categorical, but time is a continuous variable. I don't know whether it's measured in days or months or whatever the case may be, but you can see the effect of time is quite strongly significant, that cows tend to produce lower milk as they get older, indicating that it doesn't really change the coefficients for either of the dummy variables. It looks like lupins still results in significantly lower protein than barley, and barley plus lupins is borderline. But there's variation that we don't capture if we don't take into the effect, if we don't consider the effect of time. And the problem with the model on the previous slide is we're assuming that the effect of time is fixed. In other words, that's saying that the effect of time is the same for exactly every single cow. That what's the coefficient here? Minus 0.006. That for every day of the cow's life, or every month, or whatever it is, that the amount of protein produced decreases by 0.006 every day or something like that. And it may very well be that some cows' protein production levels decrease more rapidly over time and some decrease less rapidly over time, that this coefficient for time may vary from cow to cow. And it's possible to model that by adding a random slope to the model in addition to a random intercept. That in mathematical terms, if our previous model that we just fit, where we only have a fixed effect for time, we're saying the outcome variable, in this case protein, is equal to the intercept plus some coefficient of time plus the offset for diet, whether you get barley or lupins or barley plus lupins, plus a random effect for cow. Well, you could also put a random intercept or a random slope in this model, which is the same model as the previous slide, but for each cow you see there's a slope term that for cow 1 maybe the slope is larger and this B1 for the first cow is positive, or say the second cow the slope is smaller, so this term ends up being negative, whatever the case may be. Point is, under this version of the model, you don't have the same effect of time from cow to cow. The rate of decrease in protein production over time isn't the same for all the cows. It can vary randomly from cow to cow. And if you want to fit a model like that, you can use the LME command again. The difference between that and the previous models, before, recall, we said random twiddle 1 line cow. Here we say random twiddle time line cow. What that's saying is, and hopefully this notation might make a little bit more sense now. This confused me for the longest time, so don't feel bad if you're having trouble wrapping your head around it. What this is saying is that if you just say twiddle1, that says fit a random intercept for each term. Let the mean protein levels vary from cow to cow, but the effective time will be the same for all the cows. And this is saying let the effective time vary from cow to cow. And in this case, once again, it doesn't seem to change the model drastically, but, well, the biggest thing that we notice, I mean, the effects of the two diets remains about the same, but the coefficient for time became significantly smaller, went from like 0.006 to 0.12, suggesting that there is probably quite a bit of variability from cow to cow, that for some cows the decrease in protein production as they get older is quite drastic. For others it may be more or less negligible. So if you just naively average, you end up with a smaller slope than if you take into the variability from cow to cow. So in general, if you say,
so when you're doing this, you've got time in the after protein, and then you've got it also in the random section. Is that not like treating it like a random variable and a fixed variable at the same time?
okay, yeah, the question is why we have the effective time as modeled is both a random term and a fixed term. And it's really, I mean, if you think about it, we're doing essentially the same thing with the intercept, that there's a fixed intercept, which is basically the mean across all the cows, and then we have a different mean from cow to cow. You can sort of think of the overall intercept as like the mean of the means, the mean across all the cows, and the random term for the intercept. And the random effect of the intercept is taking into account that the mean levels vary from cow to cow. And here we're doing essentially the same thing with time, that the fixed effect for time just sort of represents the average decrease in the protein production over time across all the cows, but for some cows the decrease in production may be smaller, for some it may be larger. What the random effect term says is don't give this same rate of decrease for every single cow, allow some of them to have smaller rates of decrease, some of them to have larger rates of decrease. Does that make sense? Okay. And in general, if you say y twiddle x random equals twiddle x line group, that'll fit a mixed effects model to predict y based on x with a random slope for each group, where group is your grouping variable. And one question that you might ask after fitting these two models is, do you need this random slope? In general, anytime you do any type of statistical modeling, when you add more stuff to your model, you increase the variance in your model, which other things being equal will decrease the accuracy of your model. So if the slope really does vary from cow to cow, you want to take that into account or your model will be biased and also inaccurate. But if the slope is more or less the same from cow to cow, you don't want to include that term in your model because it'll just add variance to your model. So, and if you just look at output of the summary.lme command, that doesn't tell you if the random effect term is needed in the model. So, let's say we want to do a formal hypothesis test of the null hypothesis that a random slope isn't needed. You can do a scenario using the ANOVA command, sort of like we did previously, where we used the ANOVA command to see if a particular factor was needed in the model or not. The way you do it in this context is first we fit one model with the random slope, then we fit a second model without the random slope, then we do the ANOVA command to compare the two models. And you see it gives us a p-value less than 0.001. That's very strong evidence against the null hypothesis that there's no random slope. We conclude that the model is significantly better when the random slope's included. If we got a p-value of like 0.6, that would suggest that if we got a p-value of like 0.6, that would suggest that the slope is probably the same for all the cows. We don't need a random effect term to take into account the variability from cow to cow. And in general, if you say ANOVA of an LME object 1 and LME object 2, that will test the null hypothesis that these two models fit the data equally well. If you compare the two ANOVA objects like this, you want to make sure that the two objects have the same fixed effects. If they don't, then it's not really an apples to apples comparison. That you're seeing is both the fixed effect and the random effect significant, and that test turns out to be unreliable for a variety of reasons that I won't go into in this class. Basic take-home message is make sure there's no difference between the two models other than the one has the random effect that you're interested in and one doesn't. And when you're doing a mixed effects modeling, you make a series of assumptions, just like you do with linear regression, that in particular you're assuming that your error terms are approximately normally distributed with mean 0 and some unknown variance. And if this assumption is violated, then a lot of the inferences for our model can be off. This is really quite similar to the case for ordinary linear regression. We talked about like heteroskedasticity and autocorrelation and all that fun stuff. That basically heteroskedasticity is the case where this assumption of constant variance is violated. Autocorrelation is when this assumption of independence is violated. And in general, in the mixed effects world, if you don't take into account the within subject variability, the independence of your errors, your successive error terms are not going to be independent. And the hope is that by including the random effect term, you make them independent. But you can't be entirely sure of that. You want to be able to test these assumptions somehow to see if the assumption of basic, essentially random errors after making these adjustments is satisfied. Oh, the simplest way to do this in R is to just do the plot command. That we have this milk.lme1 model that has the random intercept and the random slope. If we do the plot command, as I'll show you in the next slide, it will basically plot the residuals versus the predicted values. Just like we did for ordinary linear regression, what you're hoping to see here is noise. And yeah, in general, like say, plot residuals versus predicted values, blah, blah, blah. Let's look at the plot. In this case, it looks like this, which, I mean, just eyeballing it, looks fairly decent to me. I mean, there's some indication of heteroskedasticity here. You'll notice that there seems to be more variability in the middle than there are on the sides, although even then it's hard to say if the variability really does increase in the middle, or if it's just because there's more points closer to the middle, so as a result, more extreme points. So it's hard to say, but just eyeballing this, it doesn't look particularly catastrophic. So if I saw something like this, I'd probably assume that my model is working okay and wouldn't lose too much sleep over doing inferences based on this model. Oh, I mean, as I said, it looks like it's pretty good overall. There's some possible evidence of a bulge in the middle of the model. That could be due to heteroskedasticity or curvilinearity, or it could be nothing. If I saw a plot like that, I'd use it, no problems. But if you were using this to, like, I don't know, decide when your nuclear weapons get launched or something like that, you might want to do some further testing to be absolutely certain that the model's right. And some other things to keep in mind with linear mixed effects modeling is that multicollinearity is also a possible issue if you have a bunch of correlated predictor variables, particularly if you have a large number of them, then that can increase the variance of your model, as we discussed. And it's a double whammy for mixed effects modeling because at the moment, to my knowledge, there's no software for fitting penalized regression models in the presence, and there's no software for fitting penalized regression models to fitting penalized regression mixed effects models, I think is what I'm trying to say. Blah. I mean, I know I saw a paper once where they showed how you can fit a lasso model to a linear mixed effects model, but to my knowledge, nobody's ever written any software to actually implement this, which is kind of sad because penalized regression is my preferred way to deal with the problem of collinearity. And another way that you can get around it is principal components regression, that if you just calculate the principal components of your data and fit the model to the principal components rather than the raw data, that should in principle deal with the multicollinearity issue. Or you could do something to try to simplify your data. I suppose, as much as I hate to say it, you could use stepwise modeling, which I really hate stepwise, but it would reduce the number of variables in your model and perhaps reduce the amount of multicollinearity. Even then, I question whether it's worth the potential overfitting. And other problems associated with that, given the lack of other options here, it's not something that I'm going to rule out categorically. For this class, I doubt I will give you any data that would require mixed effects modeling on the final in the first place, much less something this convoluted unless it were an extra credit question, but just in case you ever deal with this type of data in real life, I thought I should at least make you aware of the issues. You're welcome to shoot me an email or talk to some other statistician if you ever have to deal with data like this in the real world and you're not sure what to do with it. Oh, this is just a brief crash course in mixed effects modeling. It's something that you would only want to do in very simple cases. For example, if the relationship is between protein levels and time is nonlinear, which it quite likely is, this model could give you bad results. And I mean, they can and do teach entire courses on this stuff. In fact, the class right before ours that leaves all the complicated math on the board every single day, they're basically studying mixed effects models and lots of ugly glory. So I'm just barely scratching the surface of this stuff in today's lecture. If you're trying to do something other than something very simple, it's a good idea to talk to somebody who has more experience with this methodology because there's lots of things that can go wrong and it's good to know what you're doing. I mean, most of the time people don't even teach this in introductory courses because number one, it's kind of confusing, and number two, the methodology is somewhat complicated. But I mean, I just decided over the years I've had so many students in this class come to me with data sets with repeated measures where this methodology is useful. I felt like people should at least be aware that it's out there. But if you need to use it and have questions about it, you're very welcome to get in touch with me. Oh, things to remember for today: if you have repeated measures on a single experimental unit, you can use mixed effects modeling. The model building process is similar to the model building process for ordinary linear regression, and you should talk to somebody with more experience doing this sort of thing unless you're doing something relatively simple. And even if you're doing something relatively simple, it wouldn't be a bad idea to just bounce what you're doing off them to make sure they think it's reasonable. And basically the only R command to remember is the LME model, where you have this random term which tells you to include random effects in the model. Any questions about anything today? Okay, well, I guess the other announcement I forgot to make at the beginning of class is, assuming everything goes well, I'm going to try to put the final together over the weekend just to give people as much time to work on it as possible. And I'm saying it's due basically at the end of finals week. And I try not to be an ogre about deadlines, but that is one that I do have to be fairly strict on, just because there's some people in this class who may want to graduate, and that doesn't happen if I don't get my grades turned in on time. So I need to get the stuff turned in so I have time to grade it before graduation rolls around, and I'll talk more about this once the final is actually written.